All right, welcome back everyone after the coffee break. So the second talk of today is Simon Smith from University of Lincoln, and he'll be talking about infinite primitive permutation groups, Cartesian decompositions, and topologically simple locally compact groups.
Hi, well, thank you very much. Thank you for hosting me in this way. Yeah, so I'm going to talk about a sort of a link between certain just non-compact groups and finding one-ended groups in S, where S is the class of compactly generated TDLC, topologically simple non-discrete groups. And all that's linked to permutation groups. So this sort of came out of a classification theorem I did relatively recently for the subdegree finite primitive permutation groups, and Pierre Manuel asked if I could kind of explore some kind of consequences for TDLC groups. It's part of I guess a broad project to kind of try and understand better just non-compact groups through their permutation representations. So what I'll just kind of, there's a lot of things that plug into it. So I'm going to go through each of the things in this background section, but I guess the pace will be reasonably brisk so I can actually get to the meat. So yeah, so just briefly, as presumably everybody here knows, the structure theory of locally compact groups starts with the famous decomposition into the connected and totally disconnected case. And connected locally compact groups are pro-Lie, and so there's broad structures understood. And the totally disconnected locally compact groups, the TDLC groups, is where all the fun is at the moment. So a TDLC group is compactly generated if there's a compact subset that generates it abstractly. And these groups are nice because there's something like a Cayley graph, right? So there's a locally finite connected graph on which G acts as a vertex transitive group of automorphisms in a way that all its vertex stabilizers are compact and open. And so we call gamma a graph like this a Cayley-Arbels graph, and any two Cayley-Arbels graphs for a compactly generated TDLC group are quasi-isometric. And this means that we can do geometric group theory, and we can in particular talk about the ends of the group. So when I talk about the end of the group, I'm talking about the number of ends that it's that one of its Cayley-Arbels graphs has. So most of what I'll be talking about are permutation representations of these compactly generated TDLC groups. So when I'm doing that, when you picture a Cayley-Arbels graph, just picture a connected orbital graph, if you prefer permutation group theory. So the way that I like to study TDLC groups is via a completion called the Schlichting completion that gives you a natural permutation representation. And this, the Schlichting completion allows, it kind of crystallizes this geometric side of a compactly generated TDLC group. And then obviously you have the topology, and the interplay between those two things gives you their structure. So if we have a TDLC group, then by Van Danzig's theorem, it has a compact open subgroup. And so it acts on cosets of that subgroup by multiplication. And so the completion, this Schlichting completion, is you just take the permutation group induced by that action, and you consider it a topological group under the permutation topology. So the topology of pointwise convergence. So intuitively, two permutations, two things in this completion of G are close if they agree on large finite subsets of the set being acted on. So as a permutation group, this completion of G is closed in the permutation topology, it's transitive, and it's subdegree finite. So subdegree finite meaning all orbits of point stabilizers are finite. It's a natural class of permutation groups. And this Schlichter completion allows us to see the interplay between TDLC groups and the permutation groups really naturally. So under the natural topology, closed, transitive, and subdegree finite permutation groups are TDLC. And under the natural permutation representations, TDLC groups are closed, transitive, and subdegree finite. Yes, so this is a commonly used tool. So I mentioned that this talk is about the class S. So what do I mean by S? Because I guess there's two different ways that we use this, but I mean the class of topologically simple groups, so meaning no non-trivial proper closed normal subgroups that are non-discrete, compactly generated, and TDLC. So I mean totally disconnected here. Right, this class is well known to play a fundamental role in the structure theory of compactly generated TDLC groups. And so there's lots of kind of very interesting and very hard open questions about this class. And one, I suppose, that's kind of somewhat vaguely phrased here, but have we found all types of examples in S, or are they completely new constructions? So essentially, there's a handful of techniques and variations of those techniques that give us all our known types of groups in S. And you know, have we found them all? And so what I'm going to talk about is a theorem where you can kind of take a very natural class of TDLC groups and apply a test. And when you do that, you are guaranteed to have a group that has as its monolith a one-ended group in S. And so this is sort of a black box for generating groups in S from these types of examples. From these types of TDLC groups. So that's kind of one theme is thinking about this. And yeah, the other theme is just non-compact groups. So let me sort of explain what they are. So if we have first of all, I'll just say what it means to be monolithic. If we have a topological group G, and we take L to be the intersection of all its non-trivial closed normal subgroups, then we say G is monolithic with monolith L if L is non-trivial. So, a just non-compact group is a compactly generated locally compact group whose proper quotients are all compact. Well, it might be compact or it might not. If it's not compact, then it's sort of only just failing to be compact. So we call it just non-compact. So compactly generated non-compact, locally compact group whose quotients, whose proper quotients, sorry, are all compact. It's called just non-compact. So the discrete. Oh well, actually, sorry. Let me just mention this well-known theorem of Capras-Mono, which is that if you have a just non-compact group, then perhaps it's discrete, in which case it's residually finite, or it's monolithic, so it has this, this minimal closed non-trivial normal subgroup, and that monolith looks like RTN, or it's a quasi-product, so it has a direct product as a dense normal subgroup of finitely many isomorphic topologically simple factors. Now, the discrete just non-compact groups are John Wilson's just infinite groups, and they have a famous and very beautiful structure theory, and obviously the research into branch groups and everything goes into that. So yeah, there's sort of a general theme to my research at the moment is to just try to better understand these just non-compact groups. So kind of taking inspiration from the just infinite theory and try and understand just non-compact groups via their Schlichten completions, so via their natural permutation representations. Yes, so that is also kind of part of the theme of the talk. So a kind of a black box for finding one-ended groups in S and understanding a class of just non-compact groups. These are the two things that I'm going to talk about. To understand what I'm going to talk about, there's two things that I need to explain, and that's the relatively new. One's the box product, and the other is the idea behind Cartesian decompositions. And in both cases, I'll just give kind of a very light, intuitive guide. So the box product can be defined more generally than I'm going to do it, but by defining it this way, a lot of the sort of intricacies disappear and it is much more intuitive. So we're going to build it around a graph. So we're going to take a two-connected graph. So that means that we can remove any vertex from the graph and it's still connected. It's vertex transitive, meaning its automorphism group is transitive. And I'm going to pick a natural number. And I guess I want actually this number to be at least 2. So at least 2, it doesn't really make sense. So then this notation here, gamma m lambda, is going to be a connectivity 1 graph. So a graph that when you remove a vertex, the graph is no longer connected, whose lobes, so lobes are maximally 2 connected subgraphs. So the lobes are lambda and all vertices lie in m lobes. So the easiest way to see this is with some pictures rather than this sort of wordy description. So here is such a graph. So what is this graph? Well, okay, well, so let's use the notation. So what's M here? Well, we look at each vertex and we see how many lobes it lies in. So the lobes are these maximally 2 connected subgraphs. So this graph, even though I've drawn it this way, it's obviously it's vertex transitive. You can imagine, you know, a translation. These go on forever. You can imagine a translation sort of coming this way and going out there, so on and so forth. So these are the 3 lobes containing that vertex that I drew. Every vertex lies in 3 lobes, and all the lobes are 5 cycles. So 5 here, 1, 2, 3, 4, 5. Yes, 5 cycles. So our lambda is a 5 cycle, and each vertex is in 3 lobes. Here's another graph, and again, every vertex lies in 3 lobes, but the lobes this time are complete graphs on 4 vertices. Okay. So there we have it. So from that graph, we can find a subgroup of the automorphism group of that graph. And so what we do is we pick a subgroup of the automorphism group of lambda, let's call it H, and some subgroup of the symmetric group on M letters, and we want both of them to be transitive. And then the box product is a subgroup of this automorphism group satisfying the following two things. So the setwise stabilizer of any lobe in our graph, so in this group, so the setwise stabilizer in this group of any lobe in this graph has to induce H on that graph. And the stabilizer of any vertex in this group, well, each vertex lies in M lobes, and so it has to permute those M lobes, and when it does that, it induces the group F. So let's go back to those two examples, and so we can imagine what might we have here. So here we might have C5 box S3. So what would happen here? Well, this group, when we setwise stabilize, say, this lobe, we induce C5 on it. And any vertex stabilizer permutes these lobes that contain that vertex like S3. But we could equally have, you know, D10 acts on the lobes, and we could box product it with S3, or maybe even something smaller, we could box product it with C3, in which case, yeah, the local action would be like D10 this time on the lobe, or like permuting the lobes like C3. And similarly here, you know, we might have, well, what acts on K4, anything in S4, and again, S3. And so that's a group that you can picture. Notice this is actually the full automorphism group of this graph. So the box products, as I've described it, is going to be vertex transitive and transitive on lobes, and so on. So that's one construction that we need. One thing as well that we will be using later is that in this group, any subgroup there has a faithful action on a biregular tree, where the valencies of the biregular tree are the number of vertices in lambda and m. And so let's just picture that. So here we've got our graph that we've seen before. So what was that? That was gamma 3K4. And here we have a tree, and you can see that there's a sort of a correspondence between the graph and that tree. I could make, let me sort of turn this lobe into something blue, and I've got a blue vertex there that represents the lobe. And now the original vertices red. So here are the original vertices. And then of course, I've got another lobe here. And so that is this vertex, and so on and so forth. So the action of automorphism group of this graph has a faithful action on this tree. So we're going to use that in a bit. Okay, let me also mention Cartesian decompositions. So if you're interested in these at all, because I think they'll be quite useful to lots of people that are maybe listening, then I'd recommend Charles and Trevor's book. You can use the theory of Cartesian decompositions to detect product actions. So just to be clear, what do I mean by a product action? So if I've got some wreath product, and I've got some element in that wreath product, it has the kind of the imprimitive action that I suppose tends to crop up more commonly, but it also has an action on y to the m. This group is acting on y, and this is acting on m things. So if I pick an element of the group and I pick an element of the set, then the group element sends that element to the set to this. So it acts component-wise, right? G1 moves Y1 and GM moves YM. And then this element of S to M, which I haven't applied yet, permutes the components. And okay, it looks a bit messy because in the indices, then you end up with kind of inverses of sigma. So I haven't written them in, but this 1 dash and M dash is some permutation of 1 through to M. So that's what I mean by a product action. So a non-trivial homogeneous Cartesian decomposition of a set is a way of kind of picking out that action. So what you need to do is you find a finite set of partitions. So each of these is a partition of the set. And this finite set of partitions has, well, it satisfies this kind of non-triviality property, right? There's at least one partition, each partition is non-trivial, and they will have the same size. So that one is just a non-triviality condition, and this is the main condition, right? The partitions are chosen such that the partitions are chosen so that you can recover your set X from those partitions simply by intersecting parts. So you choose any part from the first partition and all the way through to the last partition, and then you intersect them and you always end up with a unique element. So yeah, if we have one of these partitions, one of these Cartesian decompositions, then we say it's preserved by a group if the partitions are permuted. Right? So maybe the parts within a partition are also permuted, but that this curly E set of partitions is permuted by G. So why is this useful? Well, on the one hand, the Rithe product in its product action on Y to the M preserves some non-trivial homogeneous Cartesian decomposition. And conversely, which is the useful one, if we have a group acting on a group of permutations of a set X, and maybe that's quite a messy action, but we manage to find some non-trivial homogeneous Cartesian decomposition on X, then G is permutationally, well, then G is a subgroup of this, permutation isomorphism. So it means that we can detect this Rithe product and product action structure for G. So as an example, so this is shamelessly taken from the book because it's such a nice, neat example. So let's imagine we've got a cube and X, Y, and Z coordinates are 0 and 1. Well, how can we partition C? So we're not looking just for any partitions. We want to pick our partitions carefully so that we can detect this product structure, so that we have this intersection property. So one thing we could do is, well, we can make one partition based on the X coordinates, right? They're either 0 or 1. We could form a second partition, sigma 2, where we partition into 2 parts according to the Y coordinate, and sigma 3 is the Z coordinate. And then, of course, every point in C is uniquely determined by its X coordinate, its Y coordinate, and its Z coordinate. So when we intersect parts of these partitions, they uniquely pick out a point in C. And so we have a non-trivial homogeneous Cartesian decomposition. And if we look at the automorphism group of C, it's C2 Rithe S3 and its product action. And what's happening here? Well, this C2 is permuting or swapping the first component of the element of C. This C2 is swapping the second, that's the Y coordinate, and this is flipping the Z coordinate, and then the S3 is interchanging those coordinate systems. So what that means then is that, that our automorphism group is preserving. So we have successfully detected this product action, which we knew was there all along. But yes, it's most useful in situations where you can't clearly see that. Okay, so now having covered the kind of background material, let me talk about what I'm going to talk about. So I'm going to be talking about TDLC groups that have, well, they all have a compact open subgroup, but specifically when you can find a compact open subgroup that's maximal. And that is going to be related to one-ended groups in S. So, so the kind of idea is that I will, well, I'll mention the theorem and then I'll kind of talk through a proof of classifying these TDLC groups according to their Schlichting completions. And then from that, we'll easily see where this comes from. So we have a non-compact TDLC group that has a compact open subgroup, of course, by Van Danzig, and we're going to assume that this compact open subgroup is a maximal subgroup in G. So I don't mean it's maximal subject to being compact and open. I mean, it really is a maximal subgroup. And okay, we're also going to assume that the Schlichting completion is non-discrete. It doesn't actually matter whether it's discrete or not, but if it's discrete, you end up with a discrete simple group, which isn't what we're looking for if we're interested in this class S. So if this completion, if this natural permutation representation satisfies these two conditions, so the first is that it preserves no non-trivial homogeneous Cartesian decomposition on the coset space, G. And if it doesn't split non-trivially as an amalgamated free product over a compact open subgroup, then, this completion is, well, it's always monolithic, and its monolith is a one-ended group in S. So it allows us to take this very natural class of TDLC groups, so those with a maximal compact open subgroup, and test for two things, and then if it satisfies them, then we end up with a one-ended group in S. And yeah, I think it's fair to say that the groups in S that are best understood are those with infinitely many ends. So this is a sort of a black box for generating, yeah, the less examples of less well-known groups in S.
Can I ask a question? Can I?
Yeah, sure.
So one-ended group in topological groups. It's
yes.
the same definition. You just remove
so
the ball.
It means it has its Cayley-Arbus graphs have one end.
The graph. Okay.
Yeah.
Cool.
And so yeah. Does that answer your question?
Yeah. Yeah.
Yes. So this is kind of what we're going to be aiming for. So at various points, maybe I realized after writing this talk that the slides get a bit dense and the arguments get a bit intricate. So if you tune out, I'll kind of, I don't know, just tune out for a bit and then reconnect when I switch to the next slide. Okay, so first of all, some sort of easy things about these groups. So TDLC group is non-compact with a compact open subgroup that's maximal. And we're going to classify them according to their Schlichting completion. So what do we have? Well, I'll put like little hints here in case someone wants to try and prove these themselves, but it's easy to show that this is just non-compact. That it's compactly generated, and because it's compactly generated, that means that it has a Cayley-Arbus graph, so we can talk about its ends, and it's primitive as a permutation group, so meaning it's well, there's lots of definitions, but yeah, transitive with maximal point stabilizers. And this is important because primitive permutation groups are sort of the atoms, the indecomposable units of permutation group theory. So usually when we're trying to do things in permutation groups, we'll start first with the primitive groups. Now yes, yeah.
Sorry, just wondering, is there a good example for G and U that we can have in mind for all these arguments?
So is there a good example for what, sorry?
For G and U?
For G and U. Yes, so I guess that's, okay, this is going to disappear when I advance to the next slide, but the automorphism group of gamma 3K4 that I gave earlier, I drew that graph earlier, that automorphism group is non-compact TDLC, and it's a point stabilizer in here. So let's take G to be that, and U to be any vertex stabilizer. G of B is maximal and compact open, and yeah, and in this case, G, the Schlichting completion is equal to the group because the group's already a permutation group.
Okay, cool, thanks.
You're welcome. So these closed subdegree finite primitive permutation groups have been classified. So that means these G over U, these completions of G, which we know are primitive. We already know from what I was talking about previously that they're closed subdegree finite permutation groups. So that means that we have a classification theorem. So we can use that classification theorem you actually end up with a very beautiful kind of classification of these TDLC groups, and then from that we can extract the theorem. Right, yeah, one thing I suppose to note is that all of these in the discrete and non-discrete cases are monolithic, and so they have this minimal closed non-trivial normal subgroup. And yeah, what I'll largely do is kind of sketch the proof of the structure theorem for G. So yeah, and it sort of analyzes a few different cases. So first of all, we could have that the monolith is non-simple. And so if it's non-simple, well, let's call it L. I guess the notation here gets a little tricky, so I'm just going to put G hat for this Schlichting completion. And U hat will be the image of U. So for those of you that prefer permutation groups, G hat's a permutation group and U hat is a point stabilizer. And L is a closed, minimal closed non-trivial normal subgroup. So using either arguments from permutation group theory or arguments, kind of Laplace monad style arguments, you can show there's a topologically simple non-abelian infinite group K in L, where K is closed to normal in L, and we can form the direct product of K with itself, so K to the M, where M is finite, and at least 2. In this case, because we're assuming non-simplicity. And this group here is dense in L, so its closure is L. And M is normal, so these are quite easy to show. Then this is much trickier. So you can obtain an action, a faithful action of K on a set Y. So from now on, I'm going to kind of, on the one hand, think of K as a subgroup of L, but on the other hand, think of it as a subgroup of the symmetric group on Y. I'm going to play kind of fast and loose with permutation isomorphisms here, just because if you keep track of them all, the notation gets a little too dense for a talk. But it has this property where we can form this nice projection. So the projection onto the first component, so remember M is this direct product, U hat is this point stabilizer. So this is really saying the point stabilizer in M and its projection onto the first component is the stabilizer in K of some element of Y. And what this does is it permanently links our kind of trivial coset U in the set being acted on, which is G over U, remember, its point stabilizer, which is U hat, is now linked permanently with this little Y in Y. And those of you that are very familiar with the finite Onad-Scott theorem will kind of recognize this condition as an important step. So we then get relatively easily that this point stabilizer U hat permutes the components of M by conjugation and induces a transitive group on M letters. So I'll call that F, just like we've been doing before. And then you can prove that there's a permutational embedding of this completion into the symmetric group on Y to the M that has the following properties. So the bijection between the two sets being acted on associates U with this, we've got the special element Y, and so we've got an obvious special element of Y to the M. So they get associated. The action of M, which remember is K to the M. So we've got this action of M on our original set that's derived from the action of our group. And, but we also have the natural product action of K to the M on Y to the M. And so our permutational isomorphism associates these two things. So I'm not going to distinguish between them from now on. And then we have a nice embedding of the point stabilizer into this homomorphic image of the normalizer in U hat of K wreath F. So where this is acting via its product action. And this homomorphism is given to you in the argument, right? So it's a specific homomorphism. It's not saying it's not an existence argument. So what this means is that we can keep track of lots of things because, so in particular, we can keep track of subdegree finiteness and all the things that we're going to need. It also means that if you're interested in TDLC groups and how they're acting, this is a very explicit embedding into the wreath product. You get to see exactly where everything's being mapped. So continuing with this case, then we can now kind of tidy things up. So sorry if I lost you there. We can take a group H to be the closure of this group in sim K, because remember this homomorphism is into sim K. If you're familiar with the finite version of the if you're familiar with the finite version of the Onad-Scott theorem, you'll notice that last step is quite complicated, and rather than just jumping to the normalizer in the full symmetric group, that's because we want to keep control of things like subdegree finiteness and that, and you lose it if you jump to the full normalizer. So then up to permutation isomorphism, we have a really nice form embedding of our completion into H wreath F in its product action. And I've written co-compact here, but it's actually a primitive subgroup, so it's much more than just co-compact. We also get to keep, by keeping track of everything, we get to see that H is non-compact TDLC with a compact open subgroup W that's maximal. So by retaining subdegree finiteness, we can extract this. So that means then that H is subject to this classification. Because remember, this is a classification of things that satisfy this exact property. Right, and H has is equal to its restricted completion because it's a permutation group and it has monolith K, so it has a topologically simple monolith. So it means it's not going to fall into this case of the analysis. And so another theme I want to draw out is this parallel between the action on lobes and the action on fibers of the Rieth product. So the action of a setwise stabilizer of this completion, acting now in its kind of cleaned up product action on Y to the M, the way it acts on any fiber, so fiber meaning, you know, some full version of Y with direct product with loads of singletons. So when you setwise stabilizer a fiber in our completion, you induce a permutation group on that fiber, and that permutation group induced is a dense subgroup of H. And when you fix a point in our completion, it permutes the fibers that contain that point, and it induces on those fibers F. And so we're going to call that, that this completion is fiber lobe full on this set. And why fiber lobe rather than just fiber? Well, we'll see that exactly the same, exactly kind of analogous things hold in a box product case, and so this term is to kind of highlight that similarity. So also we can show that this completion is one-ended. It has a if you take an orbital graph of H, if you take a Cayley-Arbus graph of H and then form a Cartesian product of itself with itself and M times, then you get a one-ended group, and it's a Cayley-Arbus graph for this completion. So it's one-ended. Okay, so that's the non-simple case dealt with. So now what if we've got a simple monolith and our group has more than one end? Well, then we can form an orbital graph. So we take as a set of vertices our original set being acted on, which we're associating with K to the M, with Y to the M, and we form arcs, so directed edges. We take a kind of an original arc, which is between 2 points in our vertex set, and then we look at all of the images under G, and that gives us our directed edge set. And because we've got the completions primitive with more than one end, then we can apply lots of power from graph theory that comes from Dunwoody's structure trees, theory of structure trees. And that means that we can choose our element G in such a way that this graph we've ended up with, this orbital graph, is one of our nice gamma M lambda graphs. And M is at least 2, and lambda in this case is primitive with at most one end. So what we have then is that our completion is contained in this automorphism group, and remember there's kind of nice subgroups of this automorphism group of box products. So let's try and pick out the box product structure. We note that any lobe stabilized, because this group is primitive, it's going to be transitive on lobes, transitive on vertices. It's any lobe stabilizer in this completion is going to induce a subgroup of the automorphism group of the lobe. And so if we take the closure of that group, then let's call that H. And vertex stabilizer, so if you stabilize a vertex in this graph, in our completion, then it's going to permute the lobes that contain that vertex, and let's call F the permutation group on S letters that's induced there. And there's no ambiguity because of the action here. These are so nicely doesn't depend on your original choice for lobe or vertex. So what that means then is that our group is contained in this box product. And by choosing H and F as we did, oh, sorry, let me also just point out that because this group is primitive, that means this is primitive, and then some arguments around the properties of the box product give you that H has to be primitive and non-cyclic. So because we picked H and F as we did, we, don't know why I keep jumping the gun and saying that. I need to make this other point first. So H here is non-compact in TDLC with a compact open subgroup that's maximal. Again, this is pulled out from the permutation, the permutation topology on this. So that means again, this H is subject to this classification that we're working through. Now I can say what I've been trying to say a few times. So we chose H so that it has this property. The action of our completion on any lobe induces a dense subgroup of H on that lobe, and the action of any point stabilizer in our completion induces F on the lobes that contain that point. And if you think back, if you switch the word lobe for fiber in our previous analysis with the Reith product, then you'll see that you're getting the same statement. So we say that this is fiber lobe full on this graph, or is a fiber lobe full subgroup of H box F. Right. So the remaining case then is that we've got a simple monolith, and our group has our completion has one end, and there we have much less to go on. This is like the almost simple case in the finite Onan-Scott theorem. So we've got the centralizer of our monolith is normal in our completion, and so we can, just like in the finite Onan-Scott theorem, we get that the centralizer is trivial or contains L. But remember, our groups K were non-abelian, so L is non-abelian, so we have to have a trivial centralizer. And that means then when our completion acts by conjugation on its subgroup, normal subgroup L, that action is faithful. So it means that we can write this, but you know, we have to be careful. This is an abstract group statement. We've lost information about when we write it this way, we lose information about the action of our group because it's not necessarily that action. And because of that, we've also lost information about the topology. The topology on these two guys is the same. This is a closed normal subgroup in this, but it's not the topology that you're getting from this. So just a warning there. Okay, so in this case, we say that this completion is almost topologically simple, borrowing language from finite groups, and by our assumption, it has precisely one end. So examples of this are we have Oshansky monsters, and you can get non-discrete examples from completions of Kac-Moody groups acting on buildings. Yes, so right, let's kind of tie it. So if I lost you, I apologize. Let's tie all this together. And so you can kind of come back to the slide now if you went awry there. If we have one of these TDLC groups that we've been analyzing, then there's a finite non-trivial transitive group, and there's another TDLC group that satisfies the conditions of what we're looking at. So having a maximal compact open subgroup, and we can classify them according to their Schlichting completion. They are either one-ended with a topologically simple, compactly generated monolith. And so if our group is non-discrete, then that monolith L will lie in the class S that we're interested in, and it'll be one-ended. So this is the one-ended almost simple case, OAS. Or it will be a type PA, which is where the completion is a primitive and therefore co-compact subgroup of H wreath S, and it's fiber lobe full. And this group H is equal to its own natural Schlichting completion, and it's of type OAS or BP. And I haven't said BP yet, but it's here, and BP stands for box product. So here we have that it's fiber lobe full subgroup of the box product, and the H in this case is either finite non-regular primitive permutation group, or it's infinite of type OAS or PA. So you can see here that we have this beautiful kind of self-referential thing going on, right? So you find your group, you look at its Schlichting completion, maybe it's of type BP, so then you know your H is finite permutation group, or it's OAS or PA. And if it's PA, you look inside and it decomposes. So your H decomposes now into, say, H naught wreath F, and your H naught is of type OAS or BP. And if it's of type BP, then you look inside and now it decomposes into maybe H1 wreath some different F, box, some different F. And you keep kind of dancing between these two. And you might wonder whether this decomposition eventually halts, but it does. So to kind of abuse the accessibility definition, it's somehow accessible as you're decomposing in this way. It always stops. So that means that we can write it in a slightly different form, where we throw out a little bit of information, but we see that it definitely terminates after finitely many steps. And it's that our completion is a primitive subgroup of this iterated wreath box, blah, 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 where each of these groups is a finite transitive permutation group. And the only sort of fancy group is this initial seed group, H0. And H0 is one of the kind of terminal cases in that classification. It's either one-ended almost simple, or it's a finite primitive non-regular permutation group. And so what does that sort of mean intuitively? Well, hopefully I can kind of show you with this diagram. So this diagram is meant to indicate a gamma m lambda, but where the lambdas are infinite. So these circles are meant to be kind of infinite lobes. And what's happening here? So let's imagine, one thing I should say is that this group here and this group here, they can be trivial if you want it to start with a box product or end in a box product. Right, let's imagine we start with one of these TDLC groups that has a maximal compact open subgroup, and we look at its Schlichting completion, and we find we find by applying the classification theorem, first of all, that it is of type BP, so it's a box product, so it has a Cayley-Albers graph, it has an orbital graph that looks like this. And then when we look in, so these lobes are one-ended, and they could be OAS, in which case we stop, but if they're not, or they could be finite and primitive and non-regular, in which case we stop, but if they're not, then they're type PA, which means they have fibers. And if you look inside at one of the fibers, so let me kind of pretend that's a fiber, and we look at that fiber is either going to be a of type BP or of type OAS. And if it's of type OAS, then we stop and we've found the kind of the seed group. But if it's not, if it's of type BP, then we have another, if it's of type BP, then we have another Cayley-Albers graph that looks like gamma m lambda for some lambda. So let me kind of draw it roughly here. It'll be, the lambda will be different, and the m will probably be different, but anyway, it will look like that. And we can start the process again. We can look at the lobes. Maybe they are one of the terminal cases, but if they're not, then we have another, we have a fiber, and we can, oh, that's not clear, we have a fiber, and we can look at that fiber and extract it and look at its Cayley-Arbels graph, and maybe it's a terminal group, in which case we stop, or maybe it isn't, and if it isn't, then we look inside it. And when you keep going and going, and then eventually you stop, because the lobes that you end up with are either OAS, derived from the Cayley-Arbels graph for a type OAS, or a finite primitive non-regular group. So that's what's going on here. Now then, so this is the last slide, and we can now relatively easily derive that theorem that's really just a corollary of the classification. If we've got a group of type BP, then we know it sits inside this automorphism group, and we already decided then, we already sort of checked that it has a faithful action on a biregular tree. And the edge stabilizers in that action, because the lambdas are locally finite and connected, the edge stabilizers are compact and open. You can prove this using properties of the box product. So that means then that we end up, this completion splits as an amalgamated free product over a compact open subgroup, just using basic Basset theory. On the other hand, if it's of type PA, then it's a product action, and we've got this. We've got this action on y to the m, and so we can extract a Cartesian decomposition using basically the same one that we did in our example, right? So we look at the projection onto the ith coordinate, and we partition according to that ith coordinate. And just like before, the intersection of a part chosen from each of these partitions will give you a unique element of y to the m. And so we have this Cartesian decomposition. And it's obviously preserved by this group, so it's preserved by our completion. And you might be looking, thinking, well, it looks like you've just found the Cartesian decomposition so easily. It's trivial, but remember that really I'm kind of fudging things here. The original action of this group was on the coset space, and there is where you would be looking for the Cartesian decomposition. It's easy for us to see it in type PA because we already know there's this permutation isomorphism into this group, and once you are in a Reith product, in product action, well, finding the natural Cartesian decomposition that's preserved by it is of course trivial. So you're hunting for it here where it will be harder to find. Anyway, yeah, now, like, obviously, let me just restate the theorem again. You know, we have our group, we have its completion. We know from our classification that it's OAS, BP, or PA. If it's BP or PA, then it preserves one of these two things. And so then if it doesn't, it has to be OAS. And if it's OAS, and we had a non-discrete Schlichten completion, then we know its monolith is one-ended in S. And that's it. So thank you very much for listening.
Thank you, Simon. Are there any questions?
Yeah, I had a question. So, so you're saying that like G is a primitive subgroup of this box Reith thing. What does that mean topologically? Is it being embedded as a closed subgroup or just continuously embedded? I mean, to put it another way, if you pull back a point stabilizer from this box Reith thing, what does it look like as a subgroup of G?
So if you, so what does, hold on, let me screen share again, and then I'll, it's probably easier if I can draw. I was a bit too keen to get my face back on screen. Where were we? So here, yeah. So you mean if you look, so are you saying if you look at a point stabilizer in here, how does it look in, how does it look?
No, the other way around. You take a point stabilizer of the group on the right and then take its pre-image in Gmod U.
If you take its pre-image in Gmod U, then it would be closed and open in Gmod U. But I wonder if you're trying to.
Would it be compact?
Yes, because so this. Yeah, because point stabilizers are compact in this group. But I wonder if you're trying to hint at something that I don't have the answer to, which is kind of tracing the behavior of this group as you descend through these box wreath.
Yeah. No,
and
I
that's
wasn't,
much.
I wasn't trying to be too clever about this. I was just thinking, like, do we preserve the topology of G? Because we've obviously changed the permutation action. It's not obvious to me that it's still acting as a closed group.
Yeah, so this, you're kind of going this way. So you're starting with your G here and your Cayley-Arbels graph of this structure is really G still acting on it in the way you would expect. They're still sharing a Cayley-Arbels graph.
Okay,
And,
right.
So the pulling back this way isn't tricky. The hard thing is tracking descendants through here. So yeah, because you're kind of taking closures of local actions all the time, then you lose track of things a little. So you can't, for example, say that this completion is fiber lobe full in this structure, but you really lose control there. It might be. I suspect that it might be, but I certainly can't prove it.
Right. Okay. And I had another question, which is, have you got any sort of candidates for OAS type groups? Like, not that you know at OAS, but you think they might be, and it's worth looking into.
Yeah. What that aren't currently known?
That aren't known to be OAS. Yeah.
Yeah. No. I think getting the OAS examples from the completions of Cat-Moody groups was kind of brutal. So I suspect that you can get them through actions on buildings, sort of like this thing that Tom de Metz has done recently, generalizing box products might be useful. I don't see that it's necessarily specific to the Cat-Moody groups acting on buildings. But yeah, I need to learn more about buildings. And as for examples that aren't kind of, just higher rank versions of things that I already know, like, no, I have no idea.
Okay, do we have any more questions for Simon? Well, seems no. So then let's thank Simon again. And let's meet again in 2 weeks.